The great dialogue between Earth and sky is perhaps the oldest conversation in existence, a relationship woven into the fabric of consciousness long before the word astronomy was ever spoken. We have always looked upward, seeking patterns in the lights, searching for signs that we are seen, that we are not alone in this vast and silent dark. For millennia, this search was guided by hope and philosophy, by stories told around fires and questions pondered in quiet chambers. It was a search for gods, for ancestors, for mythic creatures in the constellations. Then it became a search for worlds like our own. For centuries, we imagined alien life as a reflection, a distant cousin living under a similar sun on a similar rock, a being we might one day meet and recognize. We built our instruments, we sharpened our questions, we pointed our telescopes at stars that might harbor Earths, listening for a signal, a beacon, a deliberate hello. But the universe, in its infinite creativity, does not care for our expectations. It builds with the materials at hand, according to the universal laws of physics and chemistry, and it does not limit its imagination to our narrow experience. The answer to our oldest question may not arrive as a radio signal we must decode or a beacon we must find. It may not come as a visitor at our doorstep. It may arrive instead as a whisper on the solar wind, a scent carried across the interstellar void, a molecular signature written in the light of a star 120 light-years away. What if we did not find life by searching for it? What if, instead, we accidentally smelled it? 700 trillion miles from here, a distant world is leaking a gas. In the cold, thin reaches of its alien atmosphere, a molecule drifts. On Earth, this molecule, dimethyl sulfide, is a biological stain. It is the smell of the sea, the chemical breath of countless trillions of microscopic organisms smaller than a grain of sand. They produce it not as a signal, not as a purpose, but simply as waste, a byproduct of the mundane, essential business of being alive. It is the exhaust of existence. And in December of 2024, the golden eye of the James Webb Space Telescope, peering across a chasm of space and time, detected that exact molecule, that unmistakable chemical fingerprint, drifting through the atmosphere of a world known as K218b. This is not a theory. This is not a prediction scribbled on a chalkboard. This is a detection, a measurement, a data point in a spectrum of light. The confidence level, given the current evidence, is 99.7%. 3 sigma. It is a whisper that has grown into a voice we can no longer ignore. The planet K218b is not a name that rolls off the tongue with the grandeur of Atlantis or Avalon. It is a catalog number, a coordinate in a database, a speck of data that has suddenly, irrevocably, become the most interesting place in the known universe beyond our solar system. It orbits a red dwarf star in the quiet constellation of Leo. These red dwarfs are the galaxy's silent majority, smaller and cooler than our sun, burning their fuel with a frugal patience that allows them to shine for tens of billions of years, outliving sun-like stars by an order of magnitude. This particular star is young by cosmic standards, a mere few billion years old, and K218b completes its swift year, one full journey around its dim sun in just 33 Earth days. The planet resides in the star's habitable zone, that narrow, precious band of orbital real estate where temperatures theoretically permit liquid water to exist on a surface. Not so close that the world is a scorched hellscape, its oceans boiled away into steam. Not so far that it is a frozen wasteland, locked in permanent icy stasis. It is in the middle, the Goldilocks zone, where chemistry can slow down, where molecules can meet and mingle, and where complexity can begin its long, patient dance toward life. But to call K218b an Earth-like planet is to profoundly misunderstand its nature. It is not Earth. It is not even a close cousin. Picture Earth as a basketball. A sphere you can hold in your hands, feel its texture, comprehend its scale. K218b would be a vast beach ball, a bloated globe you would struggle to wrap your arms around. It has 8.6 times the mass of our world. That extra mass means stronger gravity, a constant, unyielding pull. If you weigh 150 pounds on Earth, you would weigh nearly 1,300 pounds on K218b. Every movement would be a monumental effort, like wading through concrete. Your muscles would shriek in protest. Your bones would ache under the perpetual burden, and the simple act of taking a breath would be a laborious fight against a dense, oppressive atmosphere. For the air you would be trying to draw into your lungs is nothing like the delicate, life-giving mix of nitrogen and oxygen we take for granted. K218b's atmosphere is dominated by hydrogen. It is a primordial shroud, thick and dense, pressing down on everything below with a weight we can scarcely imagine. You could not breathe it for even a single panicked moment. It is an atmosphere from the ancient past of our own solar system, a relic of planetary infancy that Earth has long since shed. But beneath this alien sky lies the strangest and most compelling part of this world. As far as our most sophisticated observations can suggest, the entire planet is covered by a single, unbroken global ocean. No mountain ranges breach the surface to become continents. No volcanic islands punctuate the endless water. No beaches, no shorelines, no land of any kind. Just liquid water in every direction, potentially hundreds of miles deep. Scientists have a name for hypothetical worlds like this: Hycean planets, hydrogen atmospheres over global oceans. Until very recently, we assumed that a habitable planet, a world that could host life, had to resemble Earth, rocky, temperate, with a nitrogen-oxygen atmosphere and land masses breaking vast seas. K218b declares that assumption to be parochial, a failure of cosmic imagination. Different structure, different atmosphere, but the same essential magical ingredient, persistent liquid water. That ocean would be an alien realm beyond our deepest earthly experiences. On Earth, the deepest trenches plunge about 7 miles down. On K218b, with its stronger gravity and potentially far deeper seas, the pressure at the bottom would be immense, monstrous. It could be enough to force water into exotic, high-pressure ice phases. Strange states of matter like ice Zix or ice Zevon, while paradoxically remaining warm due to the planet's internal heat. These are forms of water that barely exist on our planet. Curiosities confined to the extreme conditions of laboratory presses. On K218b, they could form the very floor of the world. And yet, somewhere within that vast, pressurized, lightless abyss, or perhaps near the sunlit boundary between the ocean and the thick hydrogen sky, something appears to be producing dimethyl sulfide. On Earth, This molecule is the signature of life's quiet, unthinking industry. Phytoplankton, those drifting solar-powered factories of the sea, release it as waste when they metabolize sulfur. It is not intentional. It is not a message. It is simply a chemical footnote to the process of staying alive. The gas drifts upward, escaping the sea surface, and mingles with the atmosphere, where sensitive instruments can detect its unique spectroscopic fingerprint. If the same molecule is present in the atmosphere of K218b, then life on two radically different worlds may be following the same chemical rules, stumbling upon the same metabolic pathways, leaving behind the same silent signatures in the air. For chemistry does not change from star to star. The same elements, hydrogen, carbon, oxygen, nitrogen, sulfur, behave the same way everywhere in the universe, governed by the same immutable laws. Given enough time and the right conditions, liquid water, a stable energy source, a rich soup of ingredients, similar outcomes can emerge. Not identical life, but life that solves the same chemical problems in recognizably similar ways. The temperatures on K218b, as best we can estimate, appear moderate, somewhere between 10 and 50 degrees Celsius. It is warm, but not hostile to chemistry. The planet orbits closer to its faint red sun to compensate for the star's lower energy output, hence its compact 33-day year. The result seems to be a stable world where liquid water can persist across geological epochs, and extreme temperature swings are unlikely. One can try to picture the surface of that endless ocean, a horizon that curves away in every direction, unbroken by any landmark. The water beneath, dark and deep, potentially miles deep. The sky above would not be the familiar blue of Earth, but tinted a perpetual red or orange by the light of the dwarf star. The sun itself would appear larger in the sky, closer yet dimmer, casting a muted rusty glow across the rolling waves. If life exists there, it lives under conditions we have never directly observed. Stronger gravity would shape every movement, every evolutionary adaptation for swimming or floating. A hydrogen-rich atmosphere would change the chemistry of the ocean surface and the air-sea interface. Perhaps life there never leaves the water, for what would be the point? There is no land to colonize. Perhaps it has adapted in ways we cannot yet imagine, forms and functions sculpted by an eternal, planet-wide sea. For decades, we meticulously searched for Earth-like planets. Rocky, familiar, comfortable. K218b is none of those things. It is bigger, stranger, shrouded in an atmosphere we could not breathe, and drowning in an ocean with no end. And yet, it carries a chemical signature that on our world means life. The universe is telling us that the palette for painting a living world is far broader than we dared to dream. It builds habitable environments in whatever forms physics and chemistry allow, from rocky gardens like Earth to watery globes shrouded in hydrogen. And sometimes, across an unimaginable gulf of 700 trillion miles, those worlds leave behind traces, molecular whispers drifting quietly through alien skies, waiting for a species curious enough, patient enough, and clever enough to learn how to listen to the light. The question of how life might have started on a world like K218b is a profound one, a mirror held up to our own greatest mystery. On Earth, the origin of life remains one of science's grandest unsolved puzzles. We know with certainty that it happened. The fossil evidence, The chemical fossils in ancient rocks stretch back nearly 4 billion years, to a time when the planet itself was still young and violent. But exactly how inert chemistry crossed that fundamental threshold into self-replicating, metabolizing biology is still shrouded in mystery. How did non-living molecules organize themselves into systems that could grow, reproduce, and evolve? We have multiple compelling theories. Life may have begun in warm little ponds, shallow pools, where evaporation concentrated organic building blocks. It may have sparked in the deep sea, at hydrothermal vents, where mineral-rich, superheated water provided both the chemical ingredients and the energy gradient needed to drive early reactions. Or perhaps the seeds were sown from space, with complex organic compounds forming on the icy surfaces of comets and asteroids, arriving on Earth during the heavy bombardment period, delivering the raw materials for life ready-made. K218b, a Haitian world, would allow for some of these possibilities and rule out others. There are no shallow pools on a planet with no land, no tidal zones where minerals and organics could collect and concentrate. But hydrothermal vents, they could very well exist. The planet's interior, heated by the residual energy of its formation and the decay of radioactive elements, would likely drive geological activity on the ocean floor. Hydrothermal systems, like those that support lush, sunless ecosystems on Earth's mid-ocean ridges, could be thriving in the perpetual dark of K218b's abyss. And like the early Earth, K218b would have experienced a period of intense bombardment by comets and icy planetesimals, potentially delivering water and prebiotic organic molecules from the cold depths of its planetary system. The hydrogen atmosphere itself may have been a crucial factor. The early Earth's atmosphere is thought to have been more reducing, richer in hydrogen and methane than it is today. Some origin of life experiments, like the classic Miller-Urey experiment, show that such an atmosphere sparked by lightning or UV radiation can generate amino acids and other biological building blocks with surprising ease. K218b has retained its primordial hydrogen envelope, a blanket that has never been stripped away by stellar winds or lost to space. This could have created a stable, reducing environment for billions of years, a perfect laboratory where those prebiotic reactions could proceed undisturbed, perhaps even more efficiently than they did on Earth. Time is the other essential ingredient. The star K218 is a few billion years old, and the planet itself is likely of a similar age. On Earth, life appeared with astonishing speed within the first billion years of the planet's existence, perhaps even sooner. Once established, it had 3.5 billion more years to evolve, diversify, and transform the planet. K218b has had comparable time, enough for life to emerge from the chemistry of its global ocean, adapt to the strong gravity and high pressure spread through the immense aquatic volume, and develop metabolisms suited to a hydrogen-rich, potentially sun-poor world. The sheer scale of its ocean provides an unimaginably vast theater for evolution to play out. But in the face of such tantalizing possibilities, caution is not just advisable. It is the bedrock of the scientific method. The detection of dimethyl sulfide, no matter how exciting, is not proof of life. It is evidence consistent with life. It is a clue, not a conviction. Before we can draw any definitive conclusions, scientists must rigorously ask the hard, skeptical questions. Could non-biological processes produce the same signal? Could some geological or chemical pathway we haven't yet discovered or considered generate dimethyl sulfide in such quantities without a single living cell being involved? Researchers have already begun this painstaking work, modeling the complex chemistry of sulfur compounds under high pressure and in hydrogen-rich environments, testing whether abiotic reactions could mimic a biological signature. So far, no convincing alternative has been found that adequately explains the strength and specificity of the observations. That does not mean one cannot exist. It simply means that with our current knowledge of planetary chemistry, biology remains the most parsimonious, the most straightforward explanation. It is the hypothesis that best fits the data we have in hand. But science moves forward by challenging the best hypothesis, not by blindly accepting it. The implications of this single detection, if it holds, extend far beyond the fate of one lonely ocean world 120 light-years away. K218b is not a cosmic oddity. It orbits the most common type of star in the Milky Way galaxy. Roughly 70% of the hundreds of billions of stars in our galaxy are red dwarfs like K218, and planets, we now know, are not rare. They are the galactic norm. Planets in the habitable zones of these countless red dwarfs are common. Thousands have already been identified by missions like Kepler and TESS, with thousands more waiting to be found. If one of them, a world like K218b, truly hosts life, then the emergence of life may not be an extraordinary one-in-a-trillion accident. It may be a repeatable process, a natural and perhaps even common phase in planetary evolution. Chemistry becoming biology wherever and whenever the conditions allow it to proceed. This is the fundamental shift that K218b represents. We are transitioning from the ancient philosophical question, does life exist elsewhere, to a new empirical and staggering question, how common is life in the universe? We are moving from wondering if we are a solitary miracle to realizing we may simply be one example among a vast, silent multitude. Not the living world, but a living world, one of countless islands in the cosmic archipelago where life, against all odds, found a way. Yet this raises a deeper, more technical wonder. How do we actually know any of this? How can we be certain that what we are detecting on a speck of rock and gas 700 trillion miles away is real and not an artifact, a ghost in the machine, a misreading of signals that have traveled for more than a century through the chaotic emptiness of interstellar space? The answer lies in a technique of such elegant simplicity and profound power that it borders on the miraculous. We are reading the composition of an atmosphere on a world we will never visit by watching how starlight changes as it passes through that atmosphere. We are not sending probes. We are not launching missions that take millennia. We are using light itself, the oldest messenger in the cosmos, as our informant, and the message is written not in what we see, but in what is missing. It is written in the language of absent colors. The method is called transmission spectroscopy, and its power stems from a fundamental truth of physics. Every molecule has a unique appetite for light. Just as a prism splits white light into a rainbow of colors, a spectrograph can split starlight into a detailed spectrum, a barcode of intensity across thousands of individual wavelengths. And every molecule, water vapor, carbon dioxide, methane, dimethyl sulfide, absorbs light at specific, precise wavelengths. It is a molecular fingerprint. Water vapor absorbs certain bands of infrared light. Carbon dioxide absorbs others. Methane has its own distinct pattern. We know these patterns intimately because we test them in laboratories on Earth, shining light through bottles of known gases and measuring exactly which wavelengths are diminished. The physics is universal. A molecule of dimethyl sulfide in the laboratory on Earth interacts with light in exactly the same way as a molecule of dimethyl sulfide in the atmosphere of K218b, 120 light-years distant. Its structure determines its function, and distance does not change the laws of chemistry. Now scale this up to the astronomical. K218b orbits its red dwarf star every 33 days, as seen from our vantage point. Once per orbit, from our perspective, the planet passes directly in front of its star. When it happens, the star's light dims by a tiny, almost imperceptible fraction as the planet's silhouette blocks a small portion of the stellar disk. This dimming tells us the planet's size. But here is where the magic happens. Not all of the starlight is completely blocked. A tiny sliver of light from the star's edges filters through the thin, hazy shell of the planet's atmosphere, the planetary limb, as the world begins and ends its passage. As this grazing light journeys through that thin veil of gases, hydrogen, perhaps water vapor, perhaps dimethyl sulfide, specific wavelengths are absorbed by the molecules present. The light that finally reaches us after its 120-year journey is missing those colors. It is like a rainbow with specific dark bands cut out. By analyzing the pattern of those dark bands, the absorption features, we can deduce with breathtaking precision exactly what the light encountered on its way. Consider the practical, almost poetic reality of this. A single photon leaves the surface of the star K218. It streaks into space. Instead of heading directly toward Earth, its path takes it on a grazing trajectory, skimming the upper layers of K218b's atmosphere. If its specific energy, its wavelength, matches the absorption signature of a dimethyl sulfide molecule, that molecule may capture it. The photon disappears, its energy absorbed into the chemical bonds of an alien molecule. This event happened in the year 1904. Other photons, with wavelengths that do not match any strong absorbers in that alien air, pass through unaffected. They continue their lonely journey, traveling in a straight line at 186,000 miles per second for 120 years. They cross a distance so vast it makes our entire solar system look microscopic, a distance of roughly 7.5 million times the span between the Earth and our own Sun. They travel through interstellar space, a vacuum so empty it defies human intuition. Between the stars, there may be just one atom per cubic centimeter. The air you are breathing right now contains tens of quintillions of atoms in the same volume. For 12 decades, these photons traveled through near-perfect nothingness, encountering almost nothing at all. They could have been scattered by a rare dust grain, bent by the gravity of a dark, unseen object, or altered by a magnetic field. But this particular subset of photons survived. They arrived at exactly the right place, at exactly the right time in the 2020s, and struck the 21-foot golden mirror of the James Webb Space Telescope. There, their epic journey ended. Their light was collected, focused, and fed into instruments like the near-infrared spectrograph, NIR-SPEC, and the mid-infrared instrument, MIR. The light was split into its constituent wavelengths, its energy measured with exquisitely sensitive detectors, and the data was processed by banks of computers. And scientists on a small blue planet began to read the message these ancient travelers carried: the unmistakable absence of light at specific wavelengths, the spectral fingerprint of dimethyl sulfide, one photon among trillions telling a story. But it is not one photon, it is enough of them to create a statistical signal, a pattern that rises above the noise. That is what gives us the 99.7% confidence. The signal repeats. Different transits, observed at different times, show the same missing wavelengths. Multiple instruments, looking in different parts of the infrared spectrum, confirm the pattern. This is not a one-time anomaly, not a calibration error or a glitch. It is a repeatable detection that grows stronger, more defined with every new observation. As the data accumulates, the probability of error drops. It is the slow, patient accumulation of evidence that is the hallmark of real science. Now think about what is happening on K218b at this very moment. As we speak, new photons are leaving its star. Some of them will skim the edge of the planet's atmosphere, passing through that thin shell of gas. Dimethyl sulfide molecules, if they are there, will absorb certain wavelengths. Water vapor will absorb others. The surviving photons will begin their 120-year journey toward Earth. If humanity is still here, if our civilization endures and our curiosity persists, someone will capture those photons in the year 2144 and read the information they carry. They will see K218b as it exists right now, in our present moment. And whatever happens next on that planet, a planetary scale change, the rise or fall of a biological empire, we will not see it for another 120 years. We are forever observing the past, forever delayed by the finite, if majestic, speed of light. This creates a strange and poignant temporal relationship between our world and theirs. If life exists there, and if by some further miracle it has evolved organisms advanced enough to wonder about the universe, to build their own telescopes and peer back into the void, they would be seeing Earth as it was in 1904. A planet with no artificial satellites, no globe-spanning radio noise, no city lights bright enough to register across the interstellar distance. They would see a living world, rich in oxygen and water vapor, but with no visible signs of a technological civilization. And we see them the same way, delayed by the same span of time. If intelligent life exists on K218b, we would have no way of knowing from this data. Intelligence, technology, consciousness, these are invisible at these distances. All we can detect is bulk chemistry, the presence or absence of specific molecules in the atmosphere. Light can reveal the ingredients of a biosphere, but it cannot reveal the mind that might contemplate it. The very technique that gives us this knowledge, transit spectroscopy, is itself a gift of cosmic geometry. It only works if the planet's orbital plane is aligned almost perfectly with our line of sight. Most planetary systems are not oriented this way. Most exoplanets will never transit their star from our vantage point, forever hiding their atmospheric secrets. We are fortunate, perhaps profoundly lucky, that K218b's orbit is aligned just so. This accident of alignment makes these universe-altering observations possible. Yet the window is fleeting. Each transit lasts only a few hours. The planet takes 33 days to complete an orbit, but the precious time when its atmosphere is backlit by its star is brief. During that window, telescopes like JWST must stare unblinkingly, collecting every possible photon. Miss the window, and you wait another 33 days. The James Webb Space Telescope observed multiple transits of K218b to build up the signal strength. The first showed hints, whispers in the data. The next added confirmation. The whisper grew to a murmur. After several transits, the signal became clear enough, statistically robust enough, to identify individual molecules with growing confidence. Alongside the tantalizing signature of dimethyl sulfide, the spectrum of K218b revealed other critical molecules. Water vapor was expected for an ocean world, but its detection and its abundance is a crucial piece of the puzzle. It tells us that evaporation is active, that a hydrological cycle of sorts likely operates, with liquid water at the surface cycling into the atmosphere and back again, even if the main atmospheric gas is hydrogen. Methane was also detected, and at significant levels. Methane is a double-edged sword in astrobiology. It can be a powerful biosignature produced in vast quantities by microbes on Earth, but it can also be produced abiotically through geological processes like serpentinization, where water reacts with certain rocks. By itself, methane proves nothing. What matters is the context, the combination. Carbon dioxide appeared as well, in smaller but detectable amounts. This is expected for a planet with a global ocean where carbon dioxide dissolves into water and participates in a complex chemical balance, influencing acidity and climate. Carbon is the essential backbone of complex organic molecules, and its presence, tied up in CO2 and CH4, provides the raw material life could use to build itself. Together, these gases, methane, carbon dioxide, the hint of dimethyl sulfide, and the notable absence of ammonia, form what astronomers call a biosignature ensemble. No single molecule is proof, but certain combinations, especially gases that should not coexist for long in a stable atmosphere without continuous replenishment, suggest active, dynamic processes at work. On Earth, that active process is biology. K218b lacks any detectable oxygen, which makes perfect sense in a hydrogen-rich atmosphere where any free oxygen would quickly react with hydrogen to form water and vanish. But the presence of dimethyl sulfide alongside methane and carbon dioxide in the absence of ammonia suggests an atmosphere being tugged out of chemical equilibrium by ongoing inputs from the surface or the ocean. For now, with our current models, life is the simplest explanation for maintaining that disequilibrium, though as every good scientist insists, it is not the only conceivable one. The confidence grows from consistency, from the precise alignment of prediction and observation. In laboratories on Earth, dimethyl sulfide absorbs infrared light at very specific wavelengths. In the spectrum of K218b, absorption features appear at those exact same wavelengths. The match is not approximate, it is precise. It is too precise to be a coincidence of noise or an artifact of another unknown molecule. A molecule is a molecule. Its quantum mechanical structure dictates how it interacts with photons. And this truth does not change from one corner of the galaxy to another. This universality of physics is what makes all of astronomy, all of cosmology, possible. The same laws apply everywhere. Distance does not change them. Time does not change them. The photons arriving today from K218b were emitted 120 years ago, but they carry information shaped by the same molecular processes that would occur if we could sample that atmosphere directly right now. In a very real, informational sense, we have sampled it, not by traveling there, not by sending a probe, but by decoding the universe's own data stream written in the ancient language of light. Every new transit adds another measurement, another layer of understanding. Over the coming years, we will build an increasingly detailed picture of that distant atmosphere, its composition, its stability, its temperature structure, perhaps even its seasonal changes, all from 120 light-years away, using nothing but captured starlight as our probe. The detection of dimethyl sulfide on K218b, therefore, represents far more than an exciting astronomical discovery. It is the culmination of centuries of human intellectual progress. It is the endpoint of a long chain of revelation, learning that light carries information, deciphering how atoms and molecules imprint themselves on that light, understanding the physics of stars and planets, inventing the mathematics to model it, and finally, building instruments of such staggering sensitivity and complexity that they can detect these achingly faint signals from across the galaxy. It is a story that stretches from Newton's prism to Fraunhofer's dark lines in the solar spectrum, to the quantum mechanics that explained them, to the engineers who dreamed of a telescope at Lagrange point 2. Step by logical step, generation by generation, we have inched our way to a point where we can search for life not merely by traveling outward, but by listening with unimaginable care to the light that has traveled to us. The James Webb Space Telescope, the instrument that made this discovery possible, is itself a monument to human ambition, persistence, and a stubborn refusal to accept the impossible. The project began as a concept in the mid-1990s, when visionary astronomers realized that to peer back to the first galaxies and to scrutinize the atmospheres of distant worlds, the next great observatory would have to see in the infrared. What started as a series of drawings and proposals grew over 3 decades into the most complex, delicate, and ambitious scientific instrument ever launched into space. $10 billion. 30 years of development. The careers of thousands of engineers, scientists, technicians, and administrators. A launch day that felt like the entire species holding its breath. The core challenge was one of sheer scale. To collect enough of these precious, ancient photons from incredibly faint and distant objects, the telescope needed a mirror vastly larger than any previous space telescope. The Hubble Space Telescope, which revolutionized our view of the cosmos, has a mirror about 8 feet across. JWST's primary mirror had to be over 21 feet in diameter. No rocket fairing in existence was wide enough to accommodate a solid mirror of that size. So the engineers devised a solution of breathtaking audacity, a mirror made of 18 hexagonal segments, each precision ground from lightweight beryllium and coated with a microscopically thin layer of gold for optimal infrared reflection. These segments would fold up like pieces of a sophisticated origami to fit inside the rocket for launch and then unfold and align themselves with nanometer precision in the cold darkness of space. The tolerances involved are almost incomprehensible. A human hair is about 80,000 nanometers wide. The alignment of these mirror segments had to be accurate to within a few tens of nanometers. A mistake smaller than a virus could blur the images, rendering the telescope useless. Each segment sits on a set of 7 tiny motors called actuators that can adjust its position and tilt with phenomenal precision. 126 actuators in total, all working in concert to create a single perfect optical surface out of 18 separate pieces a million miles from Earth. Beyond the mirror lay an even more daunting challenge: the sunshield. To detect the faint infrared warmth of distant planets and galaxies, the telescope itself had to be kept incredibly cold, around -400 degrees Fahrenheit. To achieve this, it needed to be shielded completely from the heat of the Sun, Earth, and Moon. The solution was a sunshield the size of a tennis court, made of 5 layers of a material thinner than a human hair. Each layer is coated to reflect sunlight, and they are separated by gaps so heat can radiate away into space without warming the layers below. The sun-facing side of this shield reaches temperatures comparable to an oven, around 200 degrees Fahrenheit. The telescope side remains in the deep, deep cold of space. A temperature difference of over 600 degrees across a structure the thickness of a few sheets of paper. And this shield, too, had to fold for launch. Hundreds of pulleys, cables, and release mechanisms all had to work perfectly, in sequence, in the vacuum of space after the violent shaking of launch. A single snagged cable, one failed latch, and the mission, 3 decades of work and $10 billion, could have ended before it began. The rocket, an Ariane 5, lifted off from French Guiana on Christmas Day, 2021. For 26 minutes, scientists and engineers around the world watched telemetry streams, hearts in throats. Any failure during ascent would mean irrevocable loss. The rocket performed flawlessly. Then began the nerve-wracking, weeks-long process of unfolding. Like a butterfly emerging from a chrysalis a million miles away, JWST slowly, autonomously transformed itself from a compact payload into a functioning observatory. The solar array deployed. The high-gain antenna unfolded. The sunshield pallets extended, and then with agonizing slowness, the 5 membranes were tensioned. Success. Then the mirror wings unfolded. Latches clicked into place. The secondary mirror deployed. More confirmations. Then came the meticulous fine alignment. Using images of a single star, engineers commanded the 126 actuators to adjust the 18 mirror segments. At first, the star appeared as 18 separate, blurry dots. Slowly, over weeks, the dots were coaxed together. They overlapped. They merged. And finally, they coalesced into a single, brilliant, razor-sharp point of light. The telescope was alive, and it saw perfectly. First light images, released in July 2022, left the world speechless. Galaxies from the dawn of time, their light stretched and reddened by the expansion of the universe, appeared in surreal detail. Nebulas, where stars are born, revealed structures hidden from all previous telescopes. The promise was real, but JWST was not built just to take breathtaking pictures. One of its primary transformative goals was exoplanet atmospheric characterization, to do exactly what it has now done with K218b. Its onboard spectrographs, like NIR-SPEC and MIRI, were designed to split infrared light into thousands of individual wavelengths and measure the brightness of each with extreme precision, hunting for the telltale absorption dips that speak of molecules. K218b was identified as a prime target early in the mission. The planet had been discovered years before by the Kepler spacecraft, detected by the periodic dimming of its star. Ground-based telescopes had measured its mass, confirming it was a sub-Neptune. It was known to be in the habitable zone, but characterizing its atmosphere, finding out what it was truly made of, required JWST's sensitivity. The first dedicated observations happened in 2023. The telescope stared at the K218 system and waited for the transit. For a few hours, it collected photons. The spectrographs did their work. The data streamed back to Earth. Initial analysis clearly showed methane and carbon dioxide. Then, in a more detailed, painstaking analysis of the subtle absorption features, the dimethyl sulfide signature emerged, faint but present, a ghost in the machine that refused to be ignored. One observation is never enough in science. Calibration errors, instrumental artifacts, random noise, all can conspire to create false signals. So JWST observed again and again. Every 33 days, when the alignment was right and the telescope's schedule permitted, it gathered more data. With each new transit, the signal-to-noise ratio improved. The picture grew clearer. The confidence level climbed from a tentative whisper to a 99.7% declaration. Scientists are now looking for other molecules, other biosignatures like dimethyl disulfide, DMDS, which was also hinted at in the data. They are building a detailed chemical profile of this alien air. The capability JWST has bestowed upon us is, when you truly contemplate it, almost magical. We can point this collection of gold and glass and silicon at a point of light 120 light-years away. We can wait for a planet, itself invisible in the glare, to pass in front of its star. And by analyzing the subtle changes in the starlight that filters through a few hundred miles of that planet's atmosphere, we can read its chemical composition. This represents the pinnacle of everything we have learned about light, optics, materials, science, cryogenics, aerospace engineering, and planetary science. Building JWST required solving problems that had no textbook solutions, creating materials that could survive the violence of launch and then operate in the profound cold and vacuum of space, writing millions of lines of software to control it, and forging international collaborations that would last longer than the careers of the people who started them. And it almost didn't happen. The project faced cancellation multiple times. Budgets ballooned, the schedules slipped by years. Technical hurdles seemed insurmountable. Critics called it a boondoggle, arguing the resources could be better spent on Earth. It survived because a community of scientists, engineers, and visionaries believed that the questions it could answer were worth the cost, the risk, and the wait. They believed that the ability to search for the chemical signatures of life on other worlds, to potentially answer the question of whether we are alone, was a goal worthy of a civilization. The detection of dimethyl sulfide on K218b is, in a very real sense, the validation of that belief. This is what JWST was built to do. This is the new era it was meant to open. Before JWST, we could only speculate about whether ocean worlds might host life. Now we can look, we can gather evidence, we can make measurements, we can do science. JWST is not looking at K218b alone. It is building a catalogue of atmospheric compositions for dozens of exoplanets, rocky super-Earths, gaseous mini-Neptunes, hot Jupiters. Each world teaches us something about how planets form, what they are made of, and where the boundaries of habitability might lie. K218b is one entry in this growing encyclopedia, but it is potentially the most profound because of that dimethyl sulfide detection. The telescope will continue operating for years, perhaps a decade or more, limited only by its fuel for station keeping. During that time, it will observe thousands of targets. But the observations of K218b will remain historic. This might be the telescope, the instrument, that first detected the chemical signature of life beyond Earth, that answered one of humanity's oldest and most haunting questions, not with philosophy, but with data. A species that learned to fly in powered, controlled flight just over a century ago can now detect specific molecules in the atmospheres of planets orbiting other stars. We went from the Wright Flyer to the James Webb Space Telescope in roughly one human lifetime. From a wooden biplane that struggled to stay airborne for a few minutes to a space observatory that can read the atmospheric composition of a world 700 trillion miles away. This trajectory of technological and intellectual progress is one of the most remarkable narratives of human civilization. And we are not done. On the drawing boards and in the imaginations of scientists are concepts for future telescopes even more powerful than JWST. The Habitable Worlds Observatory, a concept for a future flagship space telescope, would be designed with the direct imaging of Earth-like planets and the search for biosignatures like oxygen as its core mission. Larger mirrors, more sensitive instruments, broader wavelength coverage, each generation reveals what the previous one could not. JWST may have shown us dimethyl sulfide on K218b. The next generation might show us the seasonal waxing and waning of oxygen, the unmistakable red edge of extraterrestrial chlorophyll, or the industrial pollutants of a technological civilization. The search for life beyond Earth has irrevocably moved from the realm of philosophy and speculation into the domain of observational experimental science. We have the tools. We have the methods. We are beginning to have the data. K218b is likely just the first. More Hycean world candidates will be found. More atmospheric observations will be made. More potential biosignatures, some confirming, some confounding, will be detected. The catalogue of possibly living worlds will grow. With each new entry, our statistical understanding of life's prevalence in the galaxy will solidify. JWST made this possible. This magnificent machine, floating in gravitational balance at a point 1,000,000 miles from Earth, collecting infrared photons that have traveled for decades or centuries, is one of humanity's greatest achievements. It is a bridge across the void, built not of steel and stone, but of human curiosity, perseverance, and ingenuity. The light from K218b keeps arriving. Every second, new photons that left that world in 1904 complete their journey and reach Earth. Some strike JWST's golden mirror and contribute to our knowledge. Others streak past, carrying their encoded information forever onward into the expanding universe, a message in a bottle for anyone who might be watching. The stream of light is constant, a river of information flowing from the past. As long as K218b's star shines and the planet continues its transits, this data stream will persist. And somewhere in that atmosphere, if our interpretation is correct, organisms are releasing dimethyl sulfide right now. They are living their lives, metabolizing, reproducing, dying, evolving, completely unaware that 120 light-years away, a species they will never meet has built a telescope and detected their chemical exhaust. We have found them without them knowing we exist. We are watching their chemistry from across the galaxy. That is the quiet, profound power of astronomy. That is the gift JWST has given us, the ability to detect life we can never visit on a world we can never touch, using nothing but ancient starlight as our messenger and probe. On Earth, the producers of dimethyl sulfide are creatures of sublime simplicity and immense consequence. Phytoplankton, single-celled, photosynthetic organisms, so small you need a microscope to see them, yet so numerous that they form the verdant, invisible grassland of the sea. They drift in the sunlit upper layers of every ocean, using sunlight to convert carbon dioxide and water into organic matter and oxygen. They are the foundation of the marine food web, the primary producers that feed everything from tiny zooplankton to the great blue whale. And they produce much of the oxygen in our atmosphere. As a byproduct of their metabolism, specifically as they process sulfur compounds absorbed from seawater, they release dimethyl sulfide into the air. It is waste, biological exhaust, the chemical signature of microscopic life doing nothing more than surviving, growing, and reproducing. It is life's silent, fragrant footprint. On K218b, 120 light-years away, something appears to be releasing the same gas into a profoundly different atmosphere. The question that now occupies scientists, that keeps them awake, analyzing data and running models, is deceptively simple but endlessly deep. What exactly is producing it? Is it life following metabolic pathways convergent with Earth's phytoplankton? A case of universal chemistry arriving at the same solution? Is it something entirely alien that just happens to create dimethyl sulfide through a different biochemical route? Or is there some novel, non-biological geochemical process at work on that high-pressure, hydrogen-shrouded world that we, with our single planetary perspective, have not yet discovered? The biological explanation is compelling in its straightforwardness. Life on K218b could be metabolizing sulfur compounds in a manner analogous to Earth's marine microbes. The chemistry of sulfur metabolism is well understood here. Organisms take in oxidized forms of sulfur, like sulfate, from their environment. Using specialized enzymes, they reduce that sulfur, stripping away oxygen atoms and incorporating the sulfur into essential biological molecules. During this complex dance of reduction and incorporation, some of the sulfur inevitably ends up in volatile dimethyl sulfide, which then diffuses out of the cell and escapes into the environment. The process does not require staggering complexity. It is a basic metabolic trick that many simple organisms on Earth have mastered. If life exists on K218b and it follows similar chemical logic using carbon, hydrogen, oxygen, nitrogen, and sulfur as its building blocks, then dimethyl sulfide production is a perfectly reasonable expectation. The planet has a global ocean. That ocean, in contact with a rocky mantle, would undoubtedly contain dissolved sulfur compounds leached from the crust, just as Earth's oceans do. Sulfur is a common element, forged in the hearts of massive stars and scattered throughout the galaxy. Any organism living in K218 base ocean and processing nutrients would encounter sulfur. And if their metabolism includes pathways for sulfur reduction, dimethyl sulfide is a natural, almost inevitable, volatile byproduct. The organisms themselves need not be large or complex. On Earth, individual phytoplankton cells are microscopic, but their collective, planet-spanning biomass has a global impact. Trillions upon trillions of cells spread across millions of square miles of ocean surface, each releasing a minuscule amount of gas, add up to concentrations that can be detected from space. K218b could easily host similar vast populations of single-celled beings floating in the upper layers of its ocean, where the dim red light from its star can still penetrate. They would be using whatever form of photosynthesis or chemosynthesis works in their unique environment, and incidentally producing dimethyl sulfide as they go about the business of living. Their living conditions, however, would feel utterly alien by terrestrial standards. The hydrogen-rich atmosphere presses down on the ocean surface with far greater density than our own air, affecting gas exchange and surface chemistry. The stronger gravity makes buoyancy different. Organisms would not float with the same ease. The reddish, infrared heavy light from the red dwarf star provides energy at wavelengths shifted from our yellow sunlight. But none of these differences are necessarily prohibitive to life. They are simply parameters, boundary conditions to which life would adapt. Photosynthesis on K218b, if it exists, would necessarily be different. Earth's photosynthesis is fine-tuned to absorb specific wavelengths in the visible spectrum, primarily red and blue. The chlorophyll molecule is a marvel of evolutionary engineering for our sun's output. Under the glow of a red dwarf, organisms would need different photosynthetic pigments, molecules tuned to capture the longer, redder wavelengths that are actually abundant. Their entire biochemical machinery for harvesting light would be adapted to a different star. Or perhaps photosynthesis is not the dominant energy source there at all. Perhaps life on K218b relies more heavily on chemical energy welling up from the ocean itself. On Earth, we have discovered entire ecosystems that flourish in complete darkness, powered not by the sun, but by the chemistry of the planet's interior. At deep-sea hydrothermal vents, where superheated, mineral-rich water spews from cracks in the ocean floor, microbes extract energy from the reaction between hydrogen sulfide and other reduced chemicals in the vent fluid. These chemosynthetic microbes form the base of a food web that includes giant tube worms, blind shrimp, and strange clams, all thriving under immense pressure in perpetual night. K218b almost certainly has hydrothermal activity. Its interior is heated, and that heat must escape. Hydrothermal vents on its ocean floor are not just likely, they are probable. These vents would create oases of chemical energy in the vast, dark abyss. Organisms could evolve to exploit the energy gradients where hot, mineral-laden vent water mixes with the cold, deep ocean. They could feed on the chemicals flowing from the planet's heart. These chemosynthetic organisms could also produce dimethyl sulfide. The sulfur metabolism that yields DMS does not require light. It is a separate biochemical pathway. Whether an organism gets its primary energy from photons or from chemical reactions, if it processes sulfur as part of its metabolism, dimethyl sulfide can result. The potential is for a layered biosphere. In the sunlit upper ocean, photosynthetic plankton-like organisms could float, releasing DMS. In the dark depths, around hydrothermal vent fields, chemosynthetic communities could thrive, also processing sulfur and possibly contributing their own gases to the ocean, which might eventually circulate to the surface. The methane detected in K218b's atmosphere could plausibly come from methanogenic microbes in these deep, dark regions. The dimethyl sulfide could come from the sunlit plankton. Different organisms exploiting different energy sources in different niches, all contributing to the complex chemical fingerprint we see from afar. It is a picture of a potentially rich and varied biosphere, a world truly alive from its sun-dappled surface waters to its lightless volcanic depths. Yet we must temper this beautiful speculation with rigorous skepticism. Everything described is an extrapolation from a single data point. We are anthropomorphizing, or rather terraforming the universe, assuming that life elsewhere must work roughly as it does here. But life on K218b could be fundamentally different in ways we have not conceived. The basic chemistry of carbon, hydrogen, oxygen, nitrogen, and sulfur might be the same because those elements are abundant and versatile. But the implementation could be alien. Different genetic molecules instead of DNA and RNA. Different sets of amino acids building different proteins. Different cellular structures, or perhaps no discrete cells at all. Could life exist as a diffuse chemical network in the ocean, a self-organizing, metabolizing pattern in the water itself, reproducing and evolving without ever forming a membrane-bound cell? We do not know if such a thing is possible, but we cannot, from our limited perspective, rule it out. Our understanding of life's possible forms is hopelessly constrained by having seen only one example. The apparent similarity in dimethyl sulfide production could be superficial, a case of convergent chemistry rather than convergent biology. Peering deeper might reveal two forms of life so fundamentally different that comparing them is like comparing a symphony to a hurricane. The timescales, however, are permissive. K218b is a few billion years old, orbiting a star that formed in an earlier generation of the Milky Way. Life appeared on Earth within roughly the first billion years of the planet's habitable existence. If conditions on K218b became suitable early on, life there could have had 2 or 3 billion years to evolve, diversify, and adapt. That is an ocean of time, long enough for simple, single-celled organisms to potentially discover multicellularity, to form complex ecosystems, to explore evolutionary pathways we cannot imagine. The dimethyl sulfide signature, however, is consistent with simple microbial life, plankton-like creatures. Whether evolution on that world has produced anything analogous to our fish or squid or intelligent dolphins, we cannot tell from an atmospheric spectrum. Complexity does not necessarily announce itself in the bulk chemistry of the air. A planet could host a biosphere as rich and complex as Earth's Amazon rainforest and deep ocean combined, and still present an atmosphere dominated by microbial metabolic products. This is why the alternative explanation must be pursued with equal vigor, that some non-biological abiotic chemistry is producing the dimethyl sulfide. Scientists have begun this hard work, modeling reactions in hydrogen-rich atmospheres under high pressure exposed to the specific ultraviolet and infrared spectrum of a red dwarf star. They are asking if sulfur from volcanoes or from hydrothermal systems without life could be transformed into DMS through purely geological and photochemical processes. So far, no plausible abiotic pathway has been found that could generate the molecule in the apparent abundances suggested by the JWST data. But not found does not mean does not exist. The universe is a laboratory of almost infinite variety, hosting conditions and chemistries we have never replicated. K218b, with its unique combination of a thick hydrogen atmosphere, a global ocean, high pressure, and a specific stellar environment, might be conducting a novel chemical experiment. Some process involving minerals, water, hydrogen, and sulfur under high pressure, sparked by lightning or catalyzed by unknown surface chemistry, might produce DMS without a single living cell involved. If that is the case, the discovery on K218b would shift from a potential detection of biology to a fascinating discovery of exotic planetary chemistry. It would be a reminder that planets are complex chemical systems capable of producing surprising molecules. We would be disappointed, of course, for finding life is the grand prize. But we would also learn something invaluable, that we must be exceedingly careful when interpreting biosignatures. A molecule that is uniquely biological on Earth may not be uniquely biological everywhere. The scientific process demands that we hold both possibilities in our minds simultaneously, weighing them against the evidence. The data shows dimethyl sulfide is likely present. The most parsimonious explanation, based on our sole example, is biological production. But the less likely abiotic explanation cannot be ruled out until we understand that distant world much better than we do now. The path forward is more observations, better models, and perhaps the detection of other corroborating or contradictory biosignatures. Finding another gas, like oxygen or phosphine, alongside DMS would strengthen the biological case considerably. Conversely, if detailed geochemical modeling discovers a robust abiotic pathway for DMS under K218b's conditions, the biological interpretation would weaken. Science is a self-correcting journey. It follows the evidence wherever it leads. Right now, the evidence points suggestively toward life as the best explanation, but the journey is far from over. The organisms that might be producing dimethyl sulfide on K218b, if they are real, are living their lives in profound ignorance of Earth. They do not know we exist. They do not know that their metabolic waste has been detected from an unimaginable distance. They are simply doing what living things do, metabolizing, reproducing, competing, cooperating, evolving in response to their environment. The dimethyl sulfide they produce is just exhaust, an accidental byproduct of staying alive. They are not signaling us. They are not attempting communication. They are just being, and their being happens to create a chemical signature we can detect from 120 light-years away. There is a humble poetry in that. If, by some further wonder, intelligent life has evolved on K218b, if organisms there have developed complex nervous systems, tool use, language, science, and have turned their own instruments toward the stars, they would be facing the same profound isolation we are. The 120-year light travel time makes any meaningful conversation impossible. Send a signal today, and the response arrives in 240 years. That span encompasses the rise and fall of empires, the birth and death of generations. Any question you ask would be ancient history by the time the answer returns. Any answer they send would address a civilization that may have transformed beyond recognition. We are isolated not by the impossibility of detection, but by the tyranny of distance and the cosmic speed limit of light. We can know they might be there. We can study their atmosphere and infer their chemistry, but we cannot meet them, cannot visit, cannot exchange ideas in any time frame that matters to an individual human or alien life. The universe seems to have filled itself with the potential for life and then spaced those islands of biology so far apart that they remain forever separate, connected only by the thin, delayed thread of information carried at the speed of light. Yet, there is something profoundly significant in even that limited, one-way connection. Before these observations, K218b was an entry in a catalogue: mass, radius, orbital period, equilibrium temperature. Numbers on a chart. Now, it is a place, a world, a potential biosphere, a point in the cosmos where organisms might exist, where metabolic processes create and destroy molecules, where Darwinian evolution shapes populations over deep time. The dimethyl sulfide detection, tentative as it is, transforms how we must see that distant point of light. It is not just a planet anymore. It might be a living world, as complex and dynamic in its own way as Earth. And if K218b hosts life, then we are almost certainly not alone in the galaxy. The Milky Way contains hundreds of billions of stars. A significant fraction have planets. A fraction of those planets reside in habitable zones. If life arose independently on K218b, then the conditions and processes that allow life must be common, not rare. The universe appears to create life wherever it can. Chemistry becomes biology given the right ingredients, the right environment, and enough time. We are part of a pattern, not an exception. That realization, if confirmed, changes everything. Earth is not the living world. It is one of potentially millions, even billions of living worlds, each following its own evolutionary trajectory, each hosting organisms exquisitely adapted to local conditions, each producing its own unique atmospheric signature. Some might have oxygen-rich atmospheres like ours. Others might be hydrogen-dominated like K218b. Some might be methane worlds, or carbon dioxide worlds, or ammonia worlds. The diversity could be staggering, limited only by which chemical combinations allow for a stable liquid solvent and a persistent energy gradient. Imagine it, life under a hydrogen sky. Organisms swimming in endless oceans beneath an atmosphere we could not breathe, illuminated by the dim red light of a long-lived star on a world where gravity pulls 3 times harder than on Earth, metabolizing sulfur and releasing dimethyl sulfide into the thick air, reproducing, competing, evolving, completely unaware that 120 light-years away, a species called humans has detected their existence and is trying, with all its might, to understand what they are. The symmetry is beautiful, yet tinged with cosmic melancholy. We are both alive. We both exist in the same universe, subject to the same physical laws, made of the same elements forged in ancient stellar furnaces. We are both complex systems that process energy and information, that maintain themselves against the relentless pull of entropy, that create localized order in a universe trending toward disorder. We are both products of billions of years of cosmic evolution, stellar nucleosynthesis, planetary formation, chemical complexification, and finally, the mysterious transition to biology. We are fundamentally similar in that grand abstract sense, but we are separated by a gulf so vast that any connection beyond passive detection seems forever impossible. We will never compare notes on what life is like on our respective worlds. Never share what we have learned about the nature of reality. Never acknowledge each other's existence in any direct, mutually aware way. The hydrogen sky of K218b and the nitrogen-oxygen sky of Earth will never meet. The organisms beneath those skies will never meet. We are alone, together. Each world an isolated island in an ocean of space too wide to cross. Yet, knowing they might be there matters. It changes how we see ourselves and our planet. Our evolutionary story is not the only narrative of increasing complexity over deep time. Our existence is not unique. We are just one example of what happens when a planet has the right conditions for the right duration. That is simultaneously humbling and elevating. Humbling because we are not special in the way we once thought, the center of creation, the sole bearers of the flame of life. Elevating because we are part of something larger, a universe that seems almost eager to generate biology, to spin the wheel of evolution wherever physics and chemistry permit. The dimethyl sulfide drifting through K218b's atmosphere, if it is of biological origin, is the same molecule that drifts through Earth's air above our oceans. Universal chemistry giving rise to parallel biologies. Perhaps life, using the same atomic tools, stumbles upon the same metabolic solutions across the interstellar distances. That would suggest deep, underlying regularities in how life works, principles that transcend individual planets and emerge from the fundamental properties of matter. Or perhaps not. Maybe the similarity is a cosmic coincidence, a superficial convergence. We cannot know without closer study, and closer study with our current technology and understanding of physics is impossible across 120 light-years. So we are left with questions, beautiful, maddening, glorious questions that will drive science for generations. Is it life? What kind of life? How similar to us? How different? What does it look like? How does it reproduce? What is its evolutionary history? Does it have ecosystems, predators and prey, cooperation and competition? All the dynamics we see on Earth, or something entirely other? The answers will come slowly, if they come at all, through more observations, better instruments, decades of patient study, and the gradual construction of a chemical portrait detailed enough to constrain the possibilities. Maybe in 50 years, with a new generation of space telescopes, we will have enough data to say definitively whether the dimethyl sulfide is biological. Maybe in 100 years, we will have statistical certainty about the prevalence of such signatures in the galaxy. The process of science operates on cosmic timescales when the subjects are themselves cosmic. But the work continues. JWST keeps observing. Other telescopes add their data. Scientists analyze, model, debate, and publish. The catalogue of knowledge about K218b grows entry by careful entry. And somewhere under that alien hydrogen sky, if the biosignature interpretation is correct, organisms keep producing dimethyl sulfide, keep living their lives, keep adding to the chemical signature we are detecting from Earth. The connection persists, fragile, one-way, and mediated by ancient light, but it is real. Two worlds, linked by photons carrying information across the void. The distance to K218b is 120 light-years. That number is easy to say, but almost impossible to internalize. Light, the fastest thing in the universe, travels at 186,000 miles per second. To understand what this distance means in human terms, consider our farthest-reaching spacecraft. Voyager 1, launched in 1977, is now in interstellar space. After nearly 50 years of travel, it has covered about 15 billion miles. That sounds immense until you realize it is only about 0.2% of 1 light-year. Voyager 1 is moving at roughly 38,000 miles per hour. At that speed, reaching K218b would take approximately 2 million years. Even if we could achieve 1% of light speed, a velocity far beyond anything our current rocketry can conceive, the journey would take 12,000 years. That is the span of time from the end of the last ice age to the present. The entirety of recorded human civilization would fit within that travel time. Generation after generation would be born, live, and die aboard the ship. The mission would outlast languages, cultures, and empires. The people who finally arrived at K218b would have no living cultural connection to the people who launched the mission. Earth would be a mythic origin point in their ancient history. At 10% of light speed, still a fantastical dream, the trip drops to 1,200 years from the early Middle Ages to now. Still far too long for any individual, requiring generation ships or suspended animation we cannot engineer. Even at light speed itself, which relativity tells us is impossible for any object with mass, the journey would take 120 years. A person born on the day of launch would be long dead before arrival. Their great-grandchildren would be the ones to see it. And that is the absolute, unbreakable limit imposed by the structure of space-time itself. You cannot go faster than light. The universe does not allow it. So visiting K218b is not just difficult. With any technology we can foresee, it is effectively impossible. The distances are too vast, the timescales too long, human lifespans too short. We can detect that world. We can study it from afar. We can know it exists. But we cannot go there. We cannot walk on its non-existent surface, dive into its ocean, sample its water, or examine its potential organisms under a microscope. We cannot confirm life through direct observation. Communication faces the same impassable barrier. Radio waves travel at light speed. Send a message to K218b today, and it arrives in 120 years. If someone is there and replies immediately, the response comes back in another 120 years, a 240-year round trip. The person who sent the original message is dust. Their civilization may be unrecognizable. The context of the question is lost to history. Trying to have a conversation under these conditions is an exercise in futility. Each exchange takes multiple human lifetimes. Continuity shatters. The dialogue becomes a series of monologues shouted into the past, directed at ghosts. This is perhaps the universe's most profound and cruel irony. It permits life to arise on countless worlds, creates the conditions for biology to flourish on planets scattered throughout the galaxy, and gives rise to organisms capable of wonder of asking questions about their place in the cosmos. And then it spaces those worlds so far apart and limits information to the speed of light that they can never truly meet, never communicate in any meaningful time frame, never share what they have learned. We are all trapped in our local neighborhoods, able to detect our neighbors, but forever unable to visit them, to shake hands, to look into an alien eye. K218b and Earth exist simultaneously in this present moment. If life is there, organisms are metabolizing, reproducing, evolving. The two biospheres are happening in parallel, both products of billions of years of evolution, both complex systems maintaining order, but we can never compare them side by side. We can never study one from the perspective of the other, except through this delayed, filtered, incomplete information carried by light. The light we see from K218b left in 1904. If intelligent life exists there, and they are looking back at Earth with powerful telescopes, they see our world as it was in 1904. A planet before global radio, before widespread aviation, before the digital age, before the atomic bomb and the space age. They would see a world with biological signatures, but no clear signs of a technological civilization. No powerful radio leakage, no city lights, no satellite constellations. We see them the same way, K218b, as it was in 1904. If they have developed technology since then, built cities, launched spacecraft, created a globe-spanning communications network, we will not see evidence of that for another 120 years. The K218b of 2026, its present happening simultaneously with ours, is invisible to us. We only see its past. They only see ours. We are ships passing in the night of centuries, each seeing only the other's fading wake, never the ship itself. This temporal displacement layers another profound isolation on top of the spatial one. Even the information we receive is a century out of date. K218b could have changed dramatically since the photons we analyze began their journey. The organisms producing dimethyl sulfide could have gone extinct in a planetary cataclysm or evolved into new forms. The atmospheric composition could have shifted. We would not know. We will not know until the light carrying that news arrives, a century from now. Similarly, anything we learn about K218b only tells us about its past. We are always playing catch-up, always looking backward, always separated from the present state of any distant world by the immutable light travel time. This is fundamental. This is unavoidable. This is the architecture of our relativistic universe. When distances are measured in light years, this isolation extends to every potentially living world we will ever discover, each one separated by light years. Each one visible only as it was, each one unreachable except by information traveling at the speed of light. We can build a catalogue of life-bearing worlds. We can map them. We can characterize their atmospheres. But we can never visit them, never interact in real time, never bridge the gulf that separates one biosphere from another. This creates a philosophical paradox where we might be surrounded by life, by millions of living worlds throughout the galaxy, and yet remain existentially, experientially alone. Alone in the sense that we cannot reach out and touch them, cannot exchange ideas with them, cannot learn from them except through this passive, delayed observation of their atmospheric chemistry. The universe becomes a gallery of living worlds that we can look at but never enter, paintings behind glass. that we can study but never directly experience. Some find this realization deeply depressing. The idea that we might discover life is common, but connection is impossible. That we are destined to remain isolated on our pale blue dot, no matter how many other living dots glitter in the dark. That the gulf between inhabited planets is unbridgeable, not because we lack will or ingenuity, but because physics itself, the speed of light, forbids it. We are locked in place by the cosmos's own rules, confined to our local region by sheer staggering vastness. But there is another way to see it, a perspective born not of despair, but of a deeper, more poignant awe. This very isolation makes each living world infinitely more precious. If we can never visit K218b, if we can never walk through another biosphere, then Earth becomes incalculably valuable. This is the one place we can actually experience life directly. The one biosphere we can walk through, swim in, study in intimate detail, protect or destroy. Every other living world is an abstraction, knowable only through spectral graphs and atmospheric models. Earth is real, immediate, tactile, ours in a way that nowhere else can ever be. The isolation also guarantees that each biosphere evolves in pristine independence. K218b's organisms, if they exist, followed their own evolutionary path for billions of years, shaped by local conditions, producing unique solutions to the universal problems of survival and reproduction. Earth's organisms did the same. If we could catalogue all living worlds, we would see the full, breathtaking spectrum of what life can become. The entire space of biological possibility played out across billions of different environments. Each world is an independent experiment in the laboratory of the universe. That diversity has intrinsic value. If travel between worlds were easy, life might homogenize. Species from one world could invade another, ecosystems would mix, and the unique, irreplaceable character of each biosphere could be lost forever. The isolation imposed by light years is a cosmic conservation law. It preserves uniqueness. K218b will always have only K218b life. Earth will always have only Earth life. The separation maintains the independence that allows each world's evolutionary story to be its own. There is a bittersweet beauty in knowing other living worlds exist while accepting we will never visit them. We are not alone in the universe. Life is out there, on worlds scattered through the spiral arms, following the same basic chemistry, creating complex ecosystems from simple molecules and energy gradients. We can detect those worlds. We can learn about them. We can know they are there, but we cannot go there. We can only observe from afar, watching ancient light and reading chemical signatures forever separated by distances too vast for mortal beings to cross. K218b is 120 light-years away. The dimethyl sulfide we detected was produced by our clocks in 1904. Whatever organisms created that gas are likely long dead, their lives measured in days or years. Their countless descendants, however, may be producing dimethyl sulfide in what for us is the present moment of 2026. But we will not detect that for another 120 years, the K218b of 2146. When those photons arrive, we will be observing their world as it exists today. And if they are looking, they will see the Earth of 2026, 120 years from now. The cycle is eternal, an endless relay of information across the void at light speed, creating a connection between worlds that can never physically touch. Each observation is a snapshot of the distant past. Each detection tells us what was happening there when our great-great-grandparents were young. We are looking backward through time, seeing other worlds as they were, never as they are, and they, if they look, see us the same way. This is the nature of interstellar distance. Not just space, but time. Not just separation, but delay. Everything is history by the time we see it. Everything has already changed from what the light shows us. We are students of cosmic history, learning about the past of distant worlds while their present remains forever hidden, forever inaccessible. The philosophical implications are profound. We exist simultaneously with potential life on K218b, sharing the universe in the same now, but we can never share information about that now. By the time they know what Earth is like today, we will be experiencing a future they cannot see. By the time we know what K218b is like today, they will be living in a future invisible to us. We are out of sync, running on parallel tracks, but offset by the light travel time, forever unable to align our knowledge with the present reality of each other's worlds. Does this isolation diminish the staggering significance of finding life elsewhere? For some, perhaps. They might argue that discovery without the possibility of interaction is frustratingly incomplete, that knowing life exists but being unable to study it closely, to see the organisms, to understand their biology, leaves us with a maddening half-knowledge. We are limited to remote sensing, learning about alien biospheres through the narrowest of keyholes. But another perspective holds that incomplete answers are still answers. Partial knowledge is still knowledge. Knowing that dimethyl sulfide is present, that something is producing it, and that the simplest explanation is biological, tells us something universe-altering, even if it doesn't tell us everything about K218b specifically. It tells us that the phenomenon of life is likely not a fluke. It tells us that the universe seems predisposed to create it. That shift in understanding is valuable entirely on its own, independent of any practical ability to interact. The search continues despite the limitations. We will observe more transits. We will look for additional biosignatures. We will study K218b's atmosphere in ever greater detail. Each new observation adds a piece to the puzzle. Each detection constrains the possibilities. Slowly, over years and decades, we will build a portrait of that distant world. Not a complete portrait, not the intimate understanding we have of Earth, but enough to answer the most profound question: are we alone? And we will look at other planets. K218b is not the only potentially habitable world within JWST's reach. Thousands of exoplanets are known. Hundreds sit in habitable zones. JWST and its successors will observe them, searching for biosignatures, cataloging which worlds show signs of life and which do not. We are beginning a cosmic census, mapping the distribution of life across our galactic neighborhood. Each discovery will add to our understanding. If we find dimethyl sulfide on multiple Haitian worlds, that strengthens the biological explanation. If we find it only on K218b, that suggests something uniquely special about that one planet. If we find many different biosignatures on many different worlds, it tells us life is common and fantastically diverse. If biosignatures remain vanishingly rare, it tells us something else entirely about the fragility of the transition from chemistry to biology. The pattern, the statistics, matter as much as any individual stunning detection. But every world we study will suffer from the same limitation, distance. All are light years away. All observations show us the past. All potential life is unreachable. We are mapping a universe of living worlds we can never visit, cataloging biospheres we can never walk through, building knowledge of alien life we can never meet. The entire project is one of majestic, heartbreaking, remote observation. We are astronomers studying biology across interstellar distances, using starlight as our only tool. The distance to K218b is fixed. We are locked in this relationship, observing from afar, learning what we can from photons that took over a century to arrive. That is the reality the universe has given us. Not connection, but detection. Not interaction, but observation. Not meeting, but knowing. It is less than we might have dreamed in our most ambitious science fiction, but it is infinitely more than we had before telescopes like JWST existed. So we accept the limitations and work within them. We observe, analyze, learn, and build understanding piece by piece from the fragments carried by ancient light. And we marvel at what we can accomplish despite the constraints. A species confined to one small planet can still detect specific molecules on a world 700 trillion miles away, can still search for life across the galaxy, can still reach out in an informational sense and touch places that physical travel will never allow us to visit. That is remarkable. That is a testament to the human spirit of exploration and understanding, a spirit that persists even when direct exploration is forever out of reach. K218b remains distant, unreachable, isolated from Earth by a void too wide to cross. But we know it is there. We know something on that world is producing dimethyl sulfide. We know the staggering potential implications. The distance does not change those facts. The isolation does not diminish their significance. We found them even though we can never meet them. And somehow, knowing that makes the universe feel both profoundly emptier and immeasurably fuller at the same time. Emptier because the gulfs between living worlds are so heartbreakingly vast. Fuller because those worlds exist at all, scattered like rare jewels in the cosmic ocean, each one potentially hosting its own version of the miracle we call life. So here we are, somewhere out there, 120 light-years away, on a world covered in ocean beneath a hydrogen sky. Something might be alive, releasing gases, processing chemistry, existing, completely unaware that here, on a small blue planet circling a yellow star, other living things have noticed them. We found each other across the impossible distance. We detected their chemistry through the analysis of ancient starlight. And we will never meet, never communicate, never share what we have learned about the universe or acknowledge each other's existence in any direct way. Is that tragic? Or is it something else? A testament to the quiet, persistent power of life in a vast and mostly lifeless cosmos, and to the enduring curiosity of a species that longs to know its neighbors, even if only from afar. The question sits at the very heart of what the K218b discovery means. We have potentially found life beyond Earth, confirmed that we are not alone in the universe. And simultaneously, we have confirmed that we are alone in the sense that each living world remains an isolated island in its own region of space. Connection and separation, knowledge and limitation are inextricably intertwined. The answer to "Are we alone?" appears to be both no and yes, depending on how one defines alone. What we can choose is how we respond to this complex, bittersweet reality. One response is despair. The anguish of finding neighbors we can never visit, of discovering our loneliness is permanent and unbridgeable, that every biosphere is a prison defined by light years. But there is another response, another way to interpret the same immutable facts. This isolation makes each living world irreplaceable. K218b, if it has life, is the only place in the universe with K218b life. Nothing exactly like it exists anywhere else. Its evolutionary history is unique. That uniqueness has immense value. If travel were easy, ecosystems might homogenize. Earth species could spread to other planets. Alien species could arrive here. The distinct, brilliant character of each biosphere could be lost, blurred into a cosmic blandness. The isolation preserves that distinctness. K218b will only ever have K218b life. Earth will only ever have Earth life. Each world remains its own independent evolutionary experiment, showing what life becomes under a specific, unforgeable set of conditions. The universe, in its wisdom, maintains a diversity of biospheres through the very distances that keep them apart. Think what that means for Earth specifically. This planet, this biosphere, this collection of organisms and ecosystems and evolutionary lineages is one of a kind. Yes, K218b might have life. Yes, other worlds may be biologically active, but none of them are this. None have sequoia forests, or coral reefs, or elephants, or hummingbirds, or the trillions of microbes in a handful of soil. None have human consciousness with its capacity for art, science, love, and wonder. All of that is exclusively terrestrial. It evolved here. It exists here. It will never exist anywhere else unless we deliberately transplant it, which we cannot do across light years. That makes Earth precious in a way that transcends the question of whether we are alone. Even if life is common, Earth is still the sole source of Earth-type life. The only place where you can hear a bird sing at dawn, or feel moss underfoot, or gaze at the spiral of a galaxy and feel awe. Other worlds might have their own forms of beauty, their own thinkers looking up at their own stars, but they are not this beauty, not this consciousness. The K218b discovery, if it holds, shifts how we think about both commonality and uniqueness. Life might be common. The conditions for biology might arise on millions of worlds, but each instance of life is simultaneously unique, shaped by local history, following its own evolutionary path. We are part of a grand pattern and a singular exception at the same time. Common in the sense that life emerges repeatedly, unique in the sense that Earth life is unrepeatable. This beautiful duality resolves the ancient tension about whether we are special. We are, and we are not. We are not special as the universe's sole creation, but we are special as this particular creation, as this specific story written in DNA and told over 4 billion years. The dimethyl sulfide on K218b tells us that life may use similar chemistry across the light years. The same molecules, similar metabolic pathways, similar waste products. That suggests deep regularities emerging from the properties of atoms. Carbon's 4 bonds, water's polarity, sulfur's reactivity, these are universal facts. The chemistry built on them may tend toward similar outcomes. But similar chemistry does not mean identical organisms. Earth's phytoplankton and K218B's dimethyl sulfide producers might use the same metabolic trick but look utterly different, have different structures, different life cycles. The underlying chemistry converges, the biological implementation diverges in a riot of evolutionary creativity. Life finds similar solutions to universal chemical problems, but expresses those solutions through an infinite variety of forms. This is what we are learning about life through astronomy. Not just that it might exist elsewhere, but what kind of phenomenon it is. Life is chemistry that crosses a threshold into self-organization, metabolism, and reproduction. That threshold can be crossed in many places, but what emerges on the other side is shaped by a world's unique environment, energy sources, and historical accidents. Universal in principle, endlessly diverse in practice. The same basic phenomenon producing countless variations. K218b gives us one more precious data point, one more example of what life can be. If the dimethyl sulfide is biological, we are seeing life adapted to high gravity, hydrogen atmospheres, global oceans, and red dwarf starlight. That is a different set of parameters from Earth's. The adaptations will be different. The organisms will be different. But the fundamental nature of being alive, of maintaining a metabolic process against entropy, of reproducing, of evolving, that is the same. Different expressions of the same cosmic pattern, and we are part of that pattern. Earth life is not separate from it. We are the pattern expressing itself through terrestrial conditions. K218b life, if it exists, is the pattern expressing itself through Haitian world conditions. Other worlds will produce other expressions. The universe is showing us that life is something it does, a regular feature of cosmic evolution, as natural as star formation or galaxy rotation. Chemistry becomes biology when conditions allow. That happens repeatedly. We are one outcome. K218b might be another. The philosophical implications ripple outward. For most of human history, we believed life was unique to Earth. We were special, chosen, fundamentally different from a dead universe. Then, we discovered we orbit an ordinary star in an ordinary galaxy among billions. We lost our central place, but held on to the hope that life might still make us unique. The K218b discovery, and others like it, gently removes that last pedestal. We are not unique in hosting life either. We are part of a pattern, one instance of something that happens throughout the cosmos. That is humbling. It removes humanity from the center of cosmic significance. We are not the point of the universe. We are not the reason for creation. We are an outcome of natural processes, one of many such outcomes. Important to ourselves, but not particularly important to the cosmos at large. The universe would continue majestic and indifferent without us. It contains countless other worlds, some of them likely teeming with their own life, all following physical laws that do not care about human hopes or fears. But this realization is also elevating in a different way. If life is common, If the universe consistently generates biology, then being alive connects us to something larger than our individual selves or even our planetary biosphere. We are part of a universal phenomenon. We are made of star stuff, and we are one way that the universe becomes complex, aware, and curious. That is true whether we are the only instance or one of a multitude. Being common does not make life less meaningful. It makes it more profoundly meaningful, because it shows that life is a fundamental feature of reality, not a bizarre, fragile accident. The K218b discovery invites us to reconceptualize existence. We are not isolated accidents. We are expected outcomes. Given a planet with liquid water, energy, and time, life seems to emerge. It happened here. It might have happened there. It probably has happened on countless other worlds. The universe, in an impersonal, physical sense, appears inclined to create life. The laws of physics and chemistry make it almost inevitable given the right conditions. We are the result of that inevitability playing out on one particular world, around one particular star. That changes the weight of our existence. We carry forward a process that is billions of years old and operates across the galaxy. Every living thing on Earth is part of that process. And on K218b, if life is there, the same process has produced different forms. The process is universal. The outcomes are gloriously diverse. We are one outcome among many. The light from K218b keeps arriving. Every second, photons that began their journey in 1904 completed. They carry information about a world as it was then. We capture some with our telescopes, read their story, and learn. And in the year 2146, if we are still here, still wondering, we will capture photons leaving K218b today. We will see their present as our future. The cycle is eternal. A one-way flow of information across the void at light speed, connecting worlds that cannot touch. Right now, you are on Earth. This specific world with its specific life, its specific history. You are part of this biosphere made of atoms that have cycled through countless other lives over the eons. You are connected to everything alive here through deep time and shared ancestry, stretching back to the first fragile, replicating molecule. And somewhere, 120 light-years away, if our interpretation is correct, organisms are living their own version of existence. Different in detail, different in form, but the same in the fundamental phenomenon, life maintaining itself, chemistry organizing into complexity, metabolism and reproduction and adaptation unfolding. The same cosmic pattern expressing itself through different conditions. You will never meet them, never see them, never know what they are, but you know they might be there. You know that Earth's biosphere might be one of many. You know that being alive connects you not just to other Earthlings, but to a universal process that operates throughout the cosmos. You are part of something larger than you knew, part of what the universe does when chemistry becomes biology. That knowledge can sit quietly in the mind, a background hum of awe. Earth, one living world among potentially many. You, one living organism among trillions here, and countless more out there, unique and common, special and ordinary. Important to your own story, but cosmically unremarkable, except as one more instance of life's enduring pattern. And perhaps that is the truest, most peaceful perspective. Not the center of everything, but a part of everything. Not alone, but isolated. Not the only life, but the only Earth life. Connected to the cosmos through the atoms in your body and the chemistry that keeps you alive, and aware that on distant worlds other organisms might be living their own versions of this strange, beautiful experience. The universe filled itself with life and scattered it across the galaxies on countless worlds. It made sure each world's life stayed separate, evolved independently, remained unique. It created diversity through isolation. It connected everything through common physics and chemistry while keeping the living things themselves apart forever by the tyranny of distance and the speed of light. The dimethyl sulfide drifts through K218b's atmosphere right now. Molecules produced by whatever lives in those endless seas beneath that hydrogen sky. The same molecule drifts through Earth's atmosphere produced by phytoplankton in our seas. Universal chemistry. Parallel biology. Separate worlds doing similar things in different places. Never to meet, but knowable to each other through the patient, ancient language of light. That is the truth. K218b may be revealing to us. We are part of something larger, something the universe does consistently, something that transforms chemistry into complexity and complexity sometimes into consciousness. We are one instance of that something, one expression of life's grand pattern, unique in our details, but part of a universal phenomenon. And here you are on Earth, alive, part of it all, unique and common. Special and ordinary, connected and alone. That is what it means to be human in a universe where life might be everywhere, but everywhere is too far away to ever visit. That is the perspective the K218b discovery offers. Not despair at the distance, not frustration at the isolation, but acceptance of what is and wonder at what might be, and a deep, abiding gratitude for the one living world we can actually touch, experience, cherish, and call home. And that, in the end, is enough. That is everything. That is what we are. Good night.